In this presentation, I'll be explaining three-phase bridge inverter in 120-degree mode of operation, that is 120-degree conduction mode. Now, a three-phase bridge inverter is also called six-step inverter, and that is in 120-degree conduction mode. And here, each switching device that is conducting for 120 degree. And here, this is a circuit topology. Same as 180-degree conduction, the circuit topology is not changing, only the switching method is changing. And here there are three legs. In each leg there are two switches. Controlling switches are there, and this is numbered as T1, T3, T5, T2, T4 and T6. And why it is numbered in this order means the switching sequence is T1, T2, T3, T4, T5, T6, again T1, like that one. In order to make the switching sequence in that order only, this is numbered like that. This is the odd or positive group of SCRs, T1, or the controlling switch T1, T3, T5, and this is a negative group T2, T4, T6. And across each switching device, controlling device, switching controlling device, there is a feedback diode is connected. Therefore, D1, D3, D5, D2, D4 and D6. These are the feedback diodes, and these are the controlling switches T1, T3, T5, T2, T4, T6. And the DC bus voltage is marked as P. So this is a circuit topology. And what we are considering the load as a delta connected load, that is resistive load we are considering. This is the terminals of the A phases, phase A, B and C, that is connected to this delta connected load. Suppose this is a circuit, and in 120-degree conduction scheme, each device conducts for 120 degree. Previously in 180-degree conduction mode, that each device was conducting for 180-degree duration. Here, each device, that is T1 to T6, each device conducts only for 120-degree duration. And here it is preferable for a delta connected load because it provides a six-step waveform across any phase. That is, any phase means line voltage and phase voltage are same in the case of delta, and we'll be getting six-step in the sense, six transitions are there for the line voltage as well as phase voltage. Therefore, as each device conducts for 120 degree, only two devices are in conduction state at any instance, unlike 180-degree conduction scheme. In 180-degree conduction scheme, at any instant, three devices are switching devices are conducting, two from either top, one from bottom, or two from bottom or one from top. That is in the case of a 180-degree conduction scheme of a three-phase bridge inverter. But in 120-degree scheme of conduction, here only two devices will be conducting, one from the top and one from the bottom. Continuing the three-phase bridge inverter and 120-degree conduction mode, and this is the same circuit topology as shown here, and three switches, three phases or three legs are there. In each there are two switches T1, T3, T5, T2, T4 and T6. There are feedback diodes D1, D3, D5, D2, T4, D6. And the load is, we are considering a delta connected load, a balanced resistive load is connected, delta connected load is connected. Is considered here, and here these are the switching signals to T1, T2, T3, T4, T5 and T6. And we can see that each device is given triggering signal for 120-degree duration. Therefore, each device is conducting for 120-degree duration. This is 60 and this is 60. For totally 120-degree duration, T1 is conducting, and T2 is fired after 60 degree of T1 is fired. Therefore, again T2 is conducting for 160 degree. T3 is again fired after 60 degree of T2 conduction starting. Therefore, again T3 is conducting for 120 degree duration. Therefore, each device is conducting for 120 degree duration, and the switching sequence is T1, T2, T3, T4, T5, T6, and again T1, and in 60 degree interval. Therefore, switching sequence is T1, T2, T3, T4, T5, T6, again T1 in 60 degree interval. For each device conducts for 120 degree duration. Therefore, here we'll be analyzing what happens for 0 to 60 duration, 60 to 120, like that we'll be analyzing in the coming slides. Therefore, we'll be explaining later. That is, this is the voltage that is coming between the phases and line, because in delta connected, line voltage is same as the phase voltages VAB, VBC, and VCA. This is the plot. It is a 6-step. That is why it is called 6-step inverter. You can see that transitions, there are 6 transitions in there per cycle. 1, 2, 3, 4. 1, 2, 3, 4, 5. Again 6 is there. Therefore, here then only one cycle completes here. Therefore, here per cycle there are 6 changes, transitions are there. That's called 6-step inverter, and this is VAB, VBC, and VCA. Now continuing 3-phase bridge inverter, 6-step inverter in 120-degree conduction mode, and this is the circuit topology. And we have 0 to 60 degree duration. 0 to 60 degree duration, T1 and T6 are conducting. T1 and T6 are conducting means from the positive group, T1 is switched on, and from the negative group of SCR, T6 is conducting. Or here, the phase A is connected to the plus, and here phase B is connected to the negative terminal. A plus, and here B is connected to the negative terminal, and C, no switches is conducting, pulls on in this leg. Therefore, C is open. Therefore, here in order to calculate the phase voltages, you have to find out what is the VAB, what is the VBC, and what is the VCA. Now here the equivalent circuit of this one, you can see that here plus and minus comes here. Therefore, here to the between A and B, the resistance R comes. Between this part here, C is this part, 2 resistance in series comes here. Therefore, here the net voltage that is applied, voltage between VAB equal to V comes here, and voltage between A and C equal to half of this voltage, that is V by 2, and again the voltage between C and of course this VCB, or that is equal to again V by 2. The voltage is dividing in this fashion, and we'll see that corresponding phase voltage, and that's same as the line voltage, which is equal to VAB equal to this voltage, because plus point is connected to the A terminal and minus point is connected to the B terminal. Therefore, only 2 devices are conducting at any instant. Therefore, C leg at this instant, C leg is no switch off, the C leg is switched on. Therefore, here the voltage VAB equal to V, and VBC equal to, that is between VBC equal to, negative terminal is the voltage of C with respect to that is equal to minus V by 2, and similarly VCA, voltage of C with respect to A, that's also equal to minus V by 2. Therefore, these are the voltages, line voltage as well as phase voltages, that is plotted here, which is equal to, that is the VAB, V, then the other one is equal to minus V by 2, and the other one is equal to minus V by 2. This is corresponding to 0 to 60 degree duration. Now the same, if you extend to 60 to 120 degree duration, 60 to 120 degree duration, then T2 is fired. Then when T2 is the incoming SCR, T6 will be the outgoing SCR. Then during this period, T1 and T2 will be conducting. T1 and T2 will be conducting. Therefore, here T1 is conducting from the positive side, and negative side T2 is conducting. Therefore, A is connected to the plus, and C is connected to the C phase is connected to the minus. A is connected to plus and C is connected to minus, or VAC is equal to V. Now we can see that VAC equal to V, VAC, or we can say VCA. If you calculate VCA, it is equal to minus V. Similarly, VAB equal to this dividing by 2, that is V by 2, and here VBC equal to again V by 2. Suppose this is equal to V by 2, this is equal to V by 2. Voltage of C with respect to A equal to minus V. So these are again plotted here. VAB equal to V by 2, and VBC equal to again V by 2, and VCA equal to minus V. That is for 60 to 120 degree duration. Now continuing the 3-phase bridge inverter on 120 degree conduction mode. Now next is 120 to 180 degree. 120 to 180 degree, the thyristors that are conducting T2 and T3. Now here T2 and T3 is coming. T1 is outgoing SCR and T2 is the incoming SCR. T3 is fired. T3 is fired, and T1 is the outgoing SCR, and T3 is the incoming SCR. For T2 and T3 are conducting. T2 and T3 means that here T3 is conducting as well as T2 is conducting. This is connected to the plus terminal of the voltage source and this is connected to the negative terminal of the voltage. C is connected to negative and B is connected to positive. Therefore, B to the phase B will be getting plus and to the phase C you will be getting minus. Therefore, in this case, VAB and similarly that is the plus and minus, that voltage, full voltage is coming between B and C, or VBC here the corresponding, here it is written here VBC equal to the voltage between plus and minus, that is equal to full voltage is coming V, and here VAB equal to, it is equal to voltage is minus VAB equal to, it is equal to minus V by 2, because here plus and here minus is coming. For voltage of this one with respect to this one, here it's equal to, therefore VAB equal to voltage of this one with respect to this one is equal to minus V by 2, and VBC means V this one, that is here, I mean the plus terminal and minus terminal, plus 10 plus voltage this V comes here, therefore that is equal to plus V, and VCA, this voltage is again VCA here, that's equal to minus V by 2. Therefore that is plotted here, that is 120 to 180, that is plotted here 120 to 180. Here it is equal to minus V by 2 and this is equal to plus V and this is also equal to minus V by 2. Then next one 180 to 240 degree. In that duration, you can say that T4 is entering and T2 is outgoing SCR and T2 is incoming SCR, and these SCRs are, two SCRs are connecting, one from the positive group, one from the negative, one from the positive group and one from the negative group, that is T3 and T4 are conducting. T3 and T4 means T3 is conducting from this positive group and T4 is conducting from the negative group. Therefore, A is connected to the negative minus of the DC source, and from the positive side, that is T3 is conducting, that is B is connected to the positive. Therefore, B is connected to the positive and A is equal to negative. Therefore, VAB will become, now it is equal, of course magnitude equal to V, but the voltage of A with respect to B is equal to minus V, that is VAB equal to minus V. Similarly, VBC is equal to, it is equal to V by 2. This voltage, because these are coming in series, which is coming in parallel to that one, therefore that is half of the voltage only. V by 2 comes here. Similarly, VCA equal to V by 2. Therefore, again that is during this, that is 180 to 240, 180 to 240, you can say that this is equal to minus V, this is equal to plus V by 2, and this is also equal to plus V by 2. Now continuing the three-phase bridge inverter, 6-step inverter, 120 degree conduction mode. The next one is 240 to 300 degree duration. In that one, T4 and T5 are conducting. T4 and T5 are conducting. T5 is the incoming SCR. Of course, T3 is the outgoing SCR. Therefore, T5 is coming into that one. Then T4 and T5 are conducting. Here, T4 is from the negative group of switch and T5 from the positive group. Therefore, the positive C terminal is connected to the plus terminal of the source and A terminal is connected to the negative. That is, A terminal is connected to the negative and C terminal is connected to the positive. This is a C terminal which is connected to the positive. Therefore, the voltage here, the voltage between VCA will become equal to the voltage, this is a negative and this is positive. The VCA will become, which is equal to VCA equal to plus V voltage comes. VCA full voltage comes across this one, and that is the full voltage comes here, and that is equal to VCA equal to plus V volt. That is, here can say that VCA will become now plus V volt, and then VAB equal to VAB here minus, therefore it is minus V by 2. Here it is equal to minus V by VAB equal to minus V by 2. It is equal to minus V by 2. Similarly, VBC equal to minus V by 2. VBC equal to minus V by 2. Therefore, that is the duration 240 to 300. And the last duration 300 to 360 degree. 300 to 360 degree, the SCRs conducting T5 and T6. T5 from the positive group and T6 from the negative group. In that case, T6 is entering and here T4 is outgoing. Instead of T4, T6 is coming, or incoming SCR equal to T6 and outgoing SCR equal to T4. For T5 and T6 are there. T5 and T6, T5 from the positive and T6 from the negative side. For the positive side, it is equal to, here we can say that positive side C is plus here, and negative side here it is B is disconnected to B. B is negative. B is negative. B is negative. C is plus. Now let us see again the voltage between VBC is equal to minus V. It is actually the voltage of this is plus V with respect to this, or voltage of B with respect to C equal to minus V. VBC equal to minus V. And here VAB equal to V by 2. This is equal to V by 2. And VCA equal to, again VCA is again equal to V by 2. Oh, this is equal to V by 2, and this is also equal to V by 2. And the voltage of B with respect to C is equal to minus V. Therefore, VBC equal to, you can see that one, VBC equal to, here it is equal to, VBC equal to minus V. It is equal to minus V. This is one cycle complex, that is here minus V, this one. VBC equal to minus V, and VAB equal to plus V by 2, and VCA equal to plus V by 2. Therefore, then one cycle completes. Therefore, we can see that the output voltage, both phase voltage as line voltage, it is a, of course, the 6-step inverter, because 6 transitions are there. Of course, level wise it is V, 4 levels only, V by 2, minus V by 2, plus V. Only 4 levels are there, but there are 6 transitions are there. That is why it is called 6-step inverter. Now let us see the comparison of 180 degree and 120 degree conduction modes. Number of switches on. In 180 degree conduction mode, 3 switches are on at the same time. 2 from the top and 1 from the bottom, or 2 from the bottom, 1 from the top. At any time, 3 switches are switched on in the case of 180 degree conduction. But in 120 degree conduction, only 2 switches are turned on, 1 from the top and 1 from the bottom. That is the number of switches on is 3 in 180 and 2 in 120 degree conduction. And phase voltage levels. In 180 degree conduction mode, the phase voltages has 4 levels, while in 120 degree conduction mode, the phase voltages has 3 levels. Therefore, this one is phase voltage level, no, that is 3 phase, means the phase voltage has 4 levels, while in 120 degree conduction the phase voltage is 3 level. That is applicable to for a, I mean, in both cases it is a star connected load. But what I discussed in the, this 120 degree conduction mode is a delta connected one. That is why in this explanation you can see that even in the 120 degree conduction mode, you will be getting, the 4 levels in the phase voltage, and both phase and line voltage are both the same. That will be 4 levels we getting. That is the case. But in if you are considering in star type of connection, in this case in the 120 degree conduction mode, then there you will be getting only, while 120 degree conduction the phase voltage in the 3 levels only will be getting. Then voltage stress. 180 degree conduction mode, the result in lower voltage stress on the devices. Therefore, if 180 degree conduction means the voltage stress is less in the case of 180 degree conduction mode. That is when the switch is off, what is the voltage coming across that in the reverse voltage, that is less in the case of 180 degree conduction. Then output voltage, 180 degree conduction mode might produce a higher output for a given DC voltage. Output voltage is more in the case of a 180 degree conduction mode. Then application, 180 degree conduction mode is well suited for a high voltage application such as power transmission and distribution system. That is to say, 180 degree conduction mode. Continuing the comparison of 180 degree and 120 degree conduction mode. In 120 degree conduction mode, there is 60 degree interval between turn off and one thyristor and turn on the other thyristor of the same length. It provides any possibility of short circuit due to the simultaneous conduction of both devices of the same length. That possibility is there in 120 degree mode. Then utilization factor is 180 degree conduction mode is 33%, whereas 120 degree conduction mode is 28.9. That is, the utilization factor of the switch is more in the case of a 180 degree conduction. If thyristors are used in 180 degree conduction scheme, complementary voltage commutation can be used to turn off the two thyristors of the same line. In 120-degree conduction mode, auxiliary commutation is required. So these are the some comparisons of this 120-degree as well as 180-degree conduction mode of three-phase bridge inverter.